is lecture 20, and this lecture is going to be about the expanding universe. So we live in a universe that's expanding, and I'm going to talk about the history of our understanding that this is going on, and talk a bit about what it even means that we live in an expanding universe. What is it that's expanding? How do we know that it's expanding? So one kind of age-old question that's actually related somewhat to the issue that the universe is expanding is something called Olbers Paradox. And so this is what I want to start off with. Olbers Paradox is basically this one. Why is the night sky dark? So you might hear this initially and think to yourself, well, that's kind of a dumb question because the sun isn't out at night. That's why it's dark. But that's not what he meant. So Olbers, this guy Wilhelm Olbers, was a 19th century astronomer. And he posed this question, and if you think about it, it's actually a very interesting question. So the question is this. It was sort of going wisdom, or conventional wisdom at the time, that the stars were suns. Okay, the stars out there were just distant suns. And that the universe was basically infinitely big. So the universe was infinite. There were therefore an infinite number of stars. And what he said is, if that's true, then every single line of sight you would look at night should have a star somewhere along that line, if not more than one star. So if you're sitting here on Earth and you look in this direction, eventually you're going to hit a star. Similarly, this way, or this way. So imagine an infinite field of stars like this, strewn out everywhere. Somewhere along your line of sight, there's going to be a star. And that means you'll see brightness. So if this is the case, why is the night sky dark? So what do you think? Give me some answers for why this might not be true. What do you see flawed in this argument? Yeah. That's one thing he assumes, right? So that might be wrong. He says that the stars are in a uniform distribution. But I don't think that it's just that it's a uniform distribution, because even if it was kind of irregular, right? As long as it kind of went out forever, you'd eventually hit a star. Unless, I think this is where you're going, unless for some reason you get to some point and then you just run out of stars. There's like some bubble, and then out to that bubble, there's no more stars beyond that bubble. In that case, it will then get dark beyond that point. But the premise going in is that the universe is basically infinite. So it could be infinite, but stars only for some reason live around us. But that would seem kind of weird. So this is sort of the context of Olbers' paradox. He's saying, well, I'd have to construct something that was sort of bizarre, if that were the case. Anything else people can think of that might break down here? Yeah? Yeah, that's good. So they just don't shine brightly enough. So maybe... Well, I'm trying to figure this out. So if a star is out here and is not bright enough to be seen, it turns out that doesn't work. So maybe you clarify exactly what you mean. They don't shine bright enough. Think about it a little bit more. Okay, so let's keep thinking along those lines. I want people to think a bit here. I want people to give me an answer. That's good. That's a good start. The light can't travel to Earth because it's not bright enough? Yeah, sorry?
The short waves that we see can't travel.
So what is it that keeps light from traveling?
All the gas and dust.
Oh, okay, that's good. So maybe there's a lot of gas and dust between us and those stars. And so that gets absorbed, and therefore we don't see them after a certain point. Very good, that's good. So maybe this is where you were going. But let me extend this a little bit, because now we know that the universe is filled with galaxies and not just stars. So even if it's true that we live in a galaxy where we're filled with gas and dust, I can just extend Olbers Paradox to galaxies. Okay, now rather than a universe of endless stars, we live in a universe of endless galaxies. So instead of these representing stars, they represent galaxies. And so now, as we look out, we're always going to see another galaxy. And then this idea that there's a lot of gas and dust in between us might be harder to believe. It might be there, but it becomes a little bit harder to believe. Does anybody have anything else? I find it really disturbing if no one has any other ideas. Yeah?
The amount of light that is given by these stars and galaxies that is received by here is very little compared to their output.
Why? Why would that be? So you said the amount of light that hits the Earth compared to their output is a lot smaller. Why would it be? Why is there so much less light hitting us?
Light that they do output goes to space itself, only a small fraction of it goes to the Earth.
Great. So you're saying, look, just like the sun is spitting out energy in all directions, and by the time it gets to the Earth, only a small fraction of it has hit us. Maybe that's what's going on. Or more generally, there's something in astronomy called the inverse square law. That as objects that are farther away, their luminosity falls off like the distance squared. Right? I think that's exactly where you're going with this. Right, so that's very good. And in fact, that's the conventional wisdom that a lot of people had in the 19th century. They said, look, even if the stars are out there, they're so far away we can't see them, because their luminosity has fallen off so much by the time it gets to us that we can't see it. Right? It turns out that is not the right answer, unfortunately. It's a great guess, but it turns out that when you work it out, that doesn't work. And that's because if the universe is infinitely big, and you just sort of assume that you have this general background of stars represented like this, as you go out to farther distances, the number of stars that sit within a small cone goes up. Okay, so imagine, for example, that you were looking out some great distance from us, okay, along some narrow cone. So if you're looking out along some narrow cone, as you go out farther and farther away, the number of stars in that cone goes up. So while every star in that cone is dimmer by 1 over the distance squared, the area subtended by, say, if you think of it as a cutting off a bit of this surface of that sphere you're looking out at, the area goes up like the distance squared to 2. So the total volume of stars that you're surveying in a given little cone goes up like the distance squared along that cone. So while the apparent brightness of each of those galaxies or stars falls off like 1 over the distance squared, that's made up for by the fact that the volume you're looking at is also going up like the distance squared. Okay? Does this make sense? So there's always more, because as you go farther away, the volume of stuff you're looking at is going up too. So even though each one is dimmer by, say, if you're 10 times farther away, each one's dimmer by a factor of 100, there are similarly 100 times more of them out there to see, because the volume you're looking out to is getting bigger and bigger and bigger. This is what Olbers pointed out. This was his point. Does that make sense? Can anyone think of anything else that might be kind of messed up about this argument? So this is not the answer. Is there anything else that he's assuming that we might break, that might break? Yeah. Well, I think you're getting to something there. Sort of, yeah. He's sort of assuming that light is traveling instantaneously, kind of. I think maybe what you're getting to, though, is a bit more precisely. He's assuming that that light has had time to get to us. So if it's traveling to us instantaneously, then obviously it's going to get to us. But if the universe has a finite age, then you're only going to be able to go out to some distance. And beyond that point, the light would not have been able to reach us yet. Does that make sense? So there are 3 possibilities that you might have, and I think we sort of hit on a lot of them here, for what might explain Olbers Paradox in a very simple way. The first is that the universe has a finite size. It's not infinitely big. Okay, that's sort of where we were going at first. That's a possibility. The second is that the universe is infinite in size, but that the stars and galaxies only live nearby us for whatever reason. For some reason, only near us do they exist. But the third reason, and the reason that has to do with this sort of expanding universe observation that we're going to talk about today, is that if the universe has a finite age, that only light from the stars that have reached us are the ones that have had time to reach us. So there might be stars beyond some region that we just have not had time to see yet. So to understand this a little bit better, imagine this example, and we sort of did this before, but if you could just magically turn out all the lights, turn all the stars off in the universe instantaneously, and then wait a second, it gets very dark, and then you turn all the stars back on, what would happen? Well, a year later, all the stars within 1 light year would be visible, but everything beyond that point would still be dark to you. Then finally, 2 years later, light from stars at exactly 2 light years would reach us. And 3 years later, light from 3 light years would reach us. And then we're just waiting and waiting and waiting for that light to reach us. And so at this point, it turns out that we have pretty good evidence that our universe is about 14 billion years old. So that means that only light from galaxies that are within something like 14 billion light years, turns out not exactly right, could have seen us, that we could see. And so that really kills the concern of Olbers Paradox, because the universe has a finite size. And as soon as you have a finite age, and as soon as the universe has a finite age, then you can no longer extend this idea of Olbers Paradox. You no longer are concerned with the fact that the night sky is dark. The night sky is dark because the universe is not infinitely old, or light does not travel at infinite speed. Does that make sense? So this question that the universe has a finite age, it turns out, is a pretty deep one, and it has to do fundamentally with the fact that we think that the universe is expanding. And that at some point in the past it was very, very small, and at that very small point we can think of that as the beginning, before any galaxies existed or any stars existed. Now you might ask, how do we know that? So it's sort of an amazing thing that we have some idea that the universe has this age. And in fact, we know the age to a really good precision. In fact, 14 billion is probably not right. It's probably something like 13.8. So we actually know the age of the universe to sort of a pretty good precision. And it's amazing that we know that, right? So how is it that we know the age of the universe, which turns out to be more than twice as old as the Earth? The universe is more than twice as old as any rock ever discovered in the solar system. How do we know that? Well, it turns out we know that by backing it out from direct observation that the universe is expanding, and that story starts with galaxies. So I want to back up a little bit and remind you of this story with galaxies. So if you recall, there was this kind of epic struggle where people were trying to interpret what these nebulae were in the sky. And eventually, people latched on to the idea that there were a bunch of these spiral nebulae out there. And it was very likely that the Milky Way itself was one of these things, and that these things are spread out all over the universe. This began to happen sort of in earnest around the year 1900. And about 15, 20 years after that, people were analyzing these galaxies, trying to figure out what they were. So they didn't know they were galaxies, they thought. They were trying to figure out if they were other galaxies or not. And one way that they tried to do this, and specifically this guy Slipher, was trying to go out and measure how fast they were moving. And he went out and he measured how fast they were moving, and he found that they were moving very quickly. They were moving way faster than the stars within the galaxy. And that was kind of the thing he was looking at. He was trying to say, look, are they moving at different speeds than the stars in the galaxy? In which case, that would argue for them not being part of the galaxy, but they're beyond the galaxy. But he found something kind of even more incredible. So he found that most of them, almost all of them, were moving fast away from us. There were a few that were moving towards us, like Andromeda, like our nearest neighbor Andromeda, but most of them, especially when you went out things that were farther away, were moving away from us. And in fact, some of them were moving at 2 million miles an hour. So these were really incredible speeds. The way he did this, and let me remind you, is that he used the redshift of their light. So he took the spectra of their light, saw these absorption lines, for example, and he saw that they were shifted in their wavelengths with respect to what they would be in a laboratory on Earth. And he interpreted these red shifts, things that were moving away, as recessional velocity. So it turns out the amount by which the wavelength of their absorption line shifted is directly proportional to the velocity. So he interpreted that redshift as a velocity, and that's how he's able to measure their recession velocities in most cases. So he relied on this kind of amazing property of light. There's a redshift that correlates with how fast the thing is moving, interpreted that as a velocity, and was finding these incredibly high velocities for these spiral nebulae. Again, remember, they're just smudges in the sky. People don't know what they are, but he's getting a glimpse that maybe this is something fundamental about the large-scale makeup of the universe. I think these things are moving so fast they can't be part of the Milky Way. So, around that time, the other thing that was happening is Edwin Hubble had resolved these Cepheid variable stars in Andromeda and demonstrated explicitly that, in fact, it was another galaxy. So we're now getting to a point where, look, these things are other systems of stars. They are truly the things that map out the large-scale universe. It's not the stars in our own galaxy. It's not that we have a universe of stars, we have a universe of galaxies. And these galaxies are all moving away from us at this incredible speed. And people didn't really know what to make of it, right? There was no coherent model, at least in Hubble's head, in Slipher's head, of what to do with this. So this is what's happening in the astronomy world around this time, between 1915 and 1925 or so. But over in the physics world, something else was going on. In 1915, Albert Einstein had published his theory of general relativity. This was his revised theory of gravity, and in the context of this theory, he said, look, the reason why gravity operates is that masses, the existence of a mass, warps space itself. And if I build a theory that couples mass to space-time in such a way that a lot of mass would bend space, I can describe all the dynamics of the solar system. I can give you a better model for what Mercury does. I predict the gravitational lensing of starlight, the bending of starlight by the sun. All of these things that are actually observed in nature, my theory does that. So it's better than Newton's theory, and it demands that space is not a static thing anymore, but it's a dynamic thing. Space itself is dynamic and can evolve. This is a radically different idea than other people had had. And so a couple years after that, he's asked himself, well, look, I have this theory of gravity. I believe it. What does it say about the universe itself on very large scales? So he realized that his theory of gravity demanded that the universe was dynamic, that the global universe was dynamic. So this is just sort of a cartoon of Einstein's equations. So he has this one side of his equation says that curved space goes like how much energy and mass is in that space. And energy and mass in that space move around within the curved space. So that's kind of this is what Einstein's theory looks like. Okay. What he found was that when he just naively set that theory up and examined what the universe did, he found that the universe would sometimes expand or sometimes contract, but regardless, it was moving and flowing and in flux. His whole universe was in flux. And Einstein found this extremely displeasing. Okay, he thought this was aesthetically not very beautiful. In his head, the universe always was and always will be. It's sort of an infinite, everlasting thing. And so this was somewhat distasteful for him, and he wasn't aware of any data that suggested that the universe was dynamic in this way. So he changed his theory. He fiddled with his beautiful general theory of relativity and added a term. And the term you can think of as sort of an anti-gravity term. he made a constant, he stuck a constant in that didn't break anything. It turns out that the theory he made was beautifully constructed via symmetries. And it sort of forced it to have this form. But he found that if he just stuck a constant in, this is effectively like adding 1, or maybe you could think of it as adding something that's like multiplying something by 1. It didn't really mess up his theory broadly, but he basically added a constant in here. And by adding a constant, he sort of it's almost like, imagine you have a door that wants to close. His constant was sort of like a doorstop, just kind of pushing up against the door to keep it closed. Just a constant force, sort of anti-gravity to keep the universe sort of steady. So he introduced this term, which is now called the cosmological constant, and by doing so, he made the universe not expand. Because to him, that just seemed crazy. This would later be called his greatest blunder. That he basically had this theory that predicted that the universe should be expanding, but then he fiddled with it and stuck in an extra term to keep it from expanding. And said, this is the cosmology I like. And so maybe this cosmological constant exists. About 10 years later, there's a very little-known Belgian priest by the name of Georges Lemaitre, who was fluent in the mathematics of general relativity. And he was actually aware of all these data on galaxy redshifts that had come out by Slipher. And he was aware of what was going on with Edwin Hubble, too. And he wrote down he used general relativity to write down his own theory of cosmology. And in that theory, he let his universe expand. And basically, he recognized that the redshifts of galaxies were completely consistent with what's being predicted in this general theory of relativity. Okay. So he said the observed galaxy redshifts were basically a signpost that the cosmos itself was expanding. And he predicted that there should be a linear relationship between galaxy velocity and the distance to those galaxies. Now, Albert Einstein thought that this was just ugly. Okay, he said, look, your calculations are correct, but your physics is abominable. Okay, this idea that you want to make your universe expand, that's just ugly. And so go back to whatever you were doing before. You shouldn't spend your time on this. Okay. So it turns out, of course, that Lemaitre was right, and eventually Einstein changed his mind. I should mention before, and I'll come back to this again, Lemaitre would later propose that all of the universe began in an infinitely dense point, what he called the primordial atom. That is, this is the first person to propose the Big Bang, too. So it's sort of interesting that a Belgian priest was both the first person to recognize that the universe expanding on large scales and to predict that the universe began at a single point that we call the Big Bang. So around this time, okay, remember in 1925, Edwin Hubble had used these Cepheid variable stars to measure distances to galaxies. Sorry, to demonstrate the galaxies were there. So, and he had this tool with Cepheid variable stars to then measure distances to these galaxies. Also in hand were velocities to these galaxies. So the next logical step for him would be to push out and now measure distances to all these other galaxies that were out there and see if there was actually any relationship to how fast the galaxies were moving and their distance. And what he found in 1929 was that there was. So what's plotted here is a plot from Edwin Hubble's paper, original paper on this. This is his plot of the velocity of a galaxy receding from us and the distances to those galaxies as he inferred from how he understood the Cepheid variable relation, the Leavitt law at that time. And what he found was that there was basically a one-to-one correlation. And the correlation that the velocity equals some constant times distance is known as Hubble's law. If you recall, when you have a straight line, right, you have y and x. If y equals constant times x, that's a straight line. So that's what he's fitting here. Y would be v, x is d, and this h naught here is the slope of that line. So this h naught, which is called the Hubble constant, is the slope of the line. The bottom line is that this relationship, the constant relationship between velocity and distance, is exactly what Lemaitre had shown should be the prediction for an expanding universe. Now, Edwin Hubble at this time never said that this means the universe is expanding. And in fact, he never ever used that term. He always said the relationship between velocity and distance. He never gave it a physical meaning. He was just very conservative and just said there's a relationship between the redshift of a galaxy and its distance. But eventually, this observation and many future observations that would push this out and clean this up would demonstrate that the universe itself seems to be expanding. And eventually, Einstein would recognize that him putting this cosmological constant in to keep his universe static was sort of a blunder. But interestingly enough, it turns out that there is now evidence that such a cosmological constant does exist. But it sort of comes in another way, in a way that would be surprising to Einstein. And again, we'll return to that in a couple lectures. Are there any questions about this? Okay. Now, this idea that there is an expanding universe would eventually lead people to start thinking about the idea of a Big Bang. That is, now the term Big Bang is sort of a loaded term, and different people use it to mean different things. But for our purposes, when I say Big Bang, I mean that there was a time in the very, very early universe, something close to 13.8 billion years ago, when the universe was very small and very hot and made up of basically elementary particles. Nothing complex existed. There were no stars, and there were no galaxies. So there was sort of a beginning state where things were very hot. And then from that point, the universe expanded and cooled since that time. So that's my working definition of what the Big Bang means. The important thing here is that if the universe is expanding now, and you assume it's always been expanding, then you can run the movie backwards. Okay, so now it's doing this, so in the past it was doing this. And so at some point in time in the past, it was so small, everything was within a very small volume, and you can think of that as the beginning. Okay, it's sort of a time t equals 0. And so when we talk about the age of the universe today, that's what we mean. We mean that how long it's been since the universe was very small and contracted into something that was effectively close to infinitely dense. Yeah?
No question. So if the universe is expanding from a small point, does that mean that it actually has a center?
No. So so I'll return to this kind of qualitative understanding of what we mean by an expanding universe at the end. But the way to think about it is not that there's a center, but that everything is the center. Okay? And I'll return to this later. This is a question that often comes up. But it's not appropriate to think about it as if you're standing back and watching a firecracker explode. Okay? Don't think of it as sort of standing here and watching a bomb go off. And now it's a natural way to think about it because that's how I've drawn it. Right? So I mean, it's sort of not your fault. But the way to think about it is everything. So everything that we're a part of and made of, our entire universe, was scrunched down into a single point. Okay? And so there is no middle. It's in some sense, everything is the middle. And I'll return to this analogy again, but one analogy that works pretty well is if you imagine that our universe were two-dimensional and confined to the surface of a balloon. Okay? Think about the surface of a balloon. Where's the center of the surface of the balloon? Oh, you're talking about the thing you blow into? Let's pretend it's a ball then. There's nothing to blow into. This ball. What's the center of a surface of a ball? Is there a center to the surface of a ball? No. And yes, everywhere. Right? So there's either no or yes, and if the answer is yes, it's just everywhere. You could pick every point on the surface of a ball, and you could think of it as the center. Or there's nothing that's really reasonably a center for the surface of a ball. So it's very possible that our universe is like that, except now it's in 3 dimensions. So you can think about your ball and imagine blowing it up or shrinking it. So you could blow that ball up, or shrink it down, and it doesn't have to be a center to the surface of the ball. The whole surface of the ball is shrinking or growing, right? But there is no center to the surface of that shrinking and glowing. So now do the impossible thing of expanding that to 3 dimensions in your mind, and then that's what we're trying to do. Okay. Now, just to sort of keep this tracking along in the realm of real data, so people didn't know exactly what to make of this, right? Some people were arguing. Einstein had not accepted that the universe was expanding at this time. Hubble did not use the words, the universe is expanding. But something interesting was going on here, so they kept pushing. Okay? And so in 1929, he had 25 galaxies on his plot. He used the Cepheid variable stars to get distances, right? And he used their recession velocities, the redshifts, to get their velocities. And he hinted at the expansion of the universe. A couple of years later, he ended up getting more data. He was going after even more distant objects to see, did this keep going on? If I look at things that are even farther away, does this keep happening, or does this break? Is this a local phenomenon? So here's his original plot from 1929. Okay? This is the distance, this is the velocity, and this is the slope of the line. Now let's take this plot, and I want to show you his new data from 2 years later on the same plot. There it is. Right? So this is all the stuff he had. He had galaxies out to a couple megaparsecs there. In 1931, he pushed it all the way out to 30 megaparsecs, the distance, and he found that things were moving 20,000 kilometers per second out there, and it just kept rising. So the more he pushed out, the faster he was seeing galaxies receding away. So it did seem that on the largest scales observable, that the universe was just expanding away at an ever faster rate. There are questions about this? Yeah. No.
Like back to the point we were talking about, if that we can like shrink the universe to like a ball, does it mean people also believe that there's something outside of the universe?
So the question is, if you could shrink the universe to a ball, does that necessarily mean that there's something outside of the universe in some higher dimension, say, that's there? No, not necessarily. It does not necessarily mean that there's some higher dimension. And in fact, we don't think that there are large high dimensions like that we're embedded within. It doesn't seem to be the case. So this is just sort of an analogy. In order to really understand it, you have to really dig into the mathematics a bit to sort of understand what the implications are. But I'm just trying to give you a few different ways of slicing and dicing it to get an intuitive sense of what we're trying to say. Yeah?
The farther away you look out at galaxies, aren't you looking at them as they were older?
Yes.
How do you know that they're expanding at that same rate?
So the question is, because you're looking at galaxies that are far away, you're seeing them as they were a very long time ago. So how do you know, then, that they are actually moving that fast now and not, just then? You don't know. But what you see is that there's no obvious trend along this line, right? So you assume that the universe is sort of fair and it's not playing a trick on you. And so when you look at galaxies here, they seem to have evolved that, have that same relation. And this thing's only 5 megaparsecs, so it's only sort of 5 or 15 million. You're seeing them as they were about 15 million years ago. And here, you're seeing them as they were like 100 million years ago. And so there's no obvious trend that it would be really tricky for nature to play this game on us where suddenly, 100 million years ago, everything was in line, but now it's not. There's no natural scale why 100 million years would be particularly interesting, where anything significant would change like that. But the fact that looking at things that are farther away is allows us to look back in time is important for tracking the expansion history of the universe. But it turns out that that's only important on sort of billions of years timescales, not millions of years timescales. And I'll get to that in the next lecture. So the straight line given by this equation is, again, equal to V equals h naught d. And this h naught is sort of the slope of this line. And today's slope has a value of something that's about 70 kilometers per second per megaparsec. Now this is Hubble's constant, and it has kind of weird units, right? It has units of kilometers per second per megaparsec. I'll return to this later, but I just want to explain why it has these weird units, okay? it has units such that if you multiply by distance, you get a velocity. And so since d is in units of megaparsecs, if you multiply this by megaparsecs, you get kilometers per second, which is a unit of velocity. So the reason why this thing looks like it has funny units is just because it has to have funny units to work out. See what I mean? Okay. I'll return to this in a little bit. Okay. So here's another picture from Hubble's relation. Does anyone notice anything kind of funny in this picture?
There's something weird.
Yeah, there's something here. Does anyone know what this might be? Gas? Yeah, good guess. No, but it's a place at one distance where things are not quite moving along this line. They're sort of scattered about it. And so things up here are moving away from us a little faster than things in the middle, and things on this side are moving a little bit more towards us than you might think. What this is, it turns out, is a cluster of galaxies. So clusters of galaxies are places where galaxies are swarming around each other and bound by their own gravity. Okay? And so it's not that every single piece of the universe is expanding, right? There's a little pocket here of galaxies that are self-bound. And that piece of space is now trapped in on itself, and it's not expanding away with the rest of the universe. It's kind of bound together in a little ball. But it's being tugged away with the general expansion of the universe. So imagine like a little pocket of space that's not expanding because there's so much gravity there, but the rest of space in between that pocket and other things is expanding out. Does that make sense? So more generally speaking, right, not everything in the universe is expanding against everything else, right? The Earth is not expanding. The solar system is not expanding. We are not expanding, right? I mean, some of us are expanding, but it's not. Just getting old. It's not that. So it's not like this gravitational thing. It's other stuff that's binding us together. And so when we say the universe is expanding, we mean in broad sense, okay? We mean in between galaxies. The space between galaxies is what's expanding. But it doesn't mean every single thing is expanding against everything else. Our galaxy is bound together and is not being torn apart by this expansion. So now, what's weird about this too is it looks like we're at the middle, right? If we look in every direction, it looks like galaxies are moving away from us. So you might ask yourself, well, does that mean we're at the center of the universe? It turns out that that's not true, or another way of saying it is we are at the center of the universe. In fact, everywhere is the center, just like the surface of the ball analogy we talked about before. So let me close with a little cartoon that took me way too long to make. So I'm going to go through it. Here I did this on PowerPoint. Okay, so just making this slide took an hour. And then I said, okay, well, I'm now going to expand by 10%. And now I'm going to expand again by 10%. Okay, see that? Aren't you impressed? So there we go. Okay, so then let's pretend like these are galaxies and the universe is expanding. Okay, here we go. Now, let's pretend we live on this galaxy. And now what I'm going to do is I'm going to expand it, and then I'm going to restack it and take my expanded image and stack it back on this guy. And pretend like I live on that galaxy, so I'm moving with it. And then I'm going to see what happens to all the other ones. All right, so then when I make my next one, I'm stacking it right there, and now look where all the other ones went. They're now moving away. And here's the next one. I restacked it, and look what happened. Okay? So look, these guys that are close are moving away. In a given amount of time, they moved that far. But these things that are farther away are moving away faster. And the reason is there's just more space to expand between this guy and this guy, between this guy and this guy. Right? Does that make sense? Now let's imagine we lived on a different galaxy. And I'm going to do the same game. Okay? Boom, boom. It's the same thing. You get exactly the same result. People living on this galaxy will also think that they're at the center of the universe. This thing is moving away really fast. This thing is moving away a little less fast, and this thing is not moving away very fast at all. But the point is that the objects that are farther away will recede away faster because there's more space in between them and you to expand. Does that make sense? And because this took me so long, we're going to do it one more time. boom, boom. Okay? All right, we'll end there and we'll pick up next time. Thanks.